Okay, we've got our two triangles. Now all we do is use the Pythagorean theorem. Simple as that. A squared plus B squared equals C squared. So R1 squared equals 108 squared plus R minus 12 squared. Square them. If I take 108 and square it, so I'm going to clear this. 108 squared. 11,664. Get rid of, move over. 11,664 plus 144. 11,808. Divided it by 24. 492. Divided by 12. 41 feet. (41 times 12), make sure I'm right here, it's 492. So this radius would be 41 feet. The other one, same thing. R2 squared. 54 squared. R2 squared. 54 squared. 2916. Plus 144. 3060. Divide it by 24. So let me clear this. 3060 divided by 24. So for that one, if I swung an arc of 10 foot 7.5, I would have what I wanted. So this is 10 feet 7.5 inches. Okay, how do I do this in the real world now? Okay, hopefully you can see the math. And this is about a 5-second, literally a 5-second operation with the ScaleMaster Pro. Okay, it takes a little bit longer with this. But you know the technique, you know the theory or the concept behind it. It's just a high school math problem put into real world application. So if I was doing this in the real world, I would grab myself a 4x8 sheet of plywood. Okay, I would measure over 54 inches twice, 9 foot. So I got an 8-foot piece here. I would grab another strip. I don't need it this wide, but I'm going to make it. This is 8 foot, that's 1 foot. That gives me my 9-foot width. Okay? I would lay them on the ground. I would put a point here and a point here. That's my 9 feet. I would take a string or a tape measure that was 10 foot 7.5. I would hold the zero end right here and I would swing an arc. So I hold the tape, swing the arc. Zero there, swing the arc. Okay, where the arcs cross is my radius point. Now we use a piece of wood with, we've got little little trammel points, we call them, that we put on the wood. They're like little points, and one holds a pencil and one just sticks in the hole. And we would set it at 10 foot 7.5, so I get a piece of wood 10 foot 7.5, put these trammel points and make a arc with those. So I would set my point end here, my pencil end here. I would walk along here, drawing a line with the pencil end, and then I would measure over 54 inches. 54 inches, and I would measure up perpendicular and make sure that that was the 12 inches I wanted, and if it was, I'm ready to cut it with a saw and either make a template or make a piece of trim. If I was using rough sawn cedar there, I could cut it and make a trim. If I was going to lay a brick arch over it, I could make a template in a form. So the mason would come and he would lay his brick with the keystone right to my nice radius form, and it would look like an arch instead of something that's got humps and bumps and flat spots in it. So it's a professional way of doing it. The guys make do in the field, but I've seen some really, really ugly looking arches when they get done. They don't think they are. But you're a professional. You're not a hack. A hack can take a piece of string and lay it on the ground and try to make it look like an arc. You've got the technique to be able to do it mathematically and make it look like a professional job. So that takes care of the arch. The arch is an arc with a certain radius. And all it is the Pythagorean theorem. So you ought to be able to handle that. So that takes care of that. Now the big box. Okay, I'm going to lay out a little house here quickly. And let me do this. I'll draw it. Okay, let's say I've got a structure. Garage is over here, family room behind it, and so on, okay? So this is a plan view on your architectural drawings. So you come through and you look at it, and I'm gonna make this thing, I'll make that 8, make that 26, make this 24, 24. And we're gonna make him, let's make that 20 plus, let's make that 30. 30, 12. 12 moves into there, 4, 8, 18. And this is 2, and this is 4. And I got 30 there, I've got 58 there. 28 there. So that's that right? That's 40, 58, that's 50, 58, that's 32. This guy, if that's 30 and that's 30, it's 2. Okay, I think that's right. That's 40 on that side and that's 40 on that side. That looks good. Okay. We've got a house. You're going to lay it out. You want somebody to come and dig a hole so that you can put your foundation for this house in. So if I go out there in the field and I start putting stakes at each corner, to show them exactly where the corner of the foundation is. So I get done, I've got all these stakes going around, and it lays out exactly where each corner is going to be. Okay, what's going to happen when the excavator comes? He's got to dig a hole bigger than the house so that the guys can get in the hole and work. They got to set forms, they got to set forms for footers, they got to set forms for walls, they got to put the waterproofing on. So the hole needs to be bigger than the house. So when we get done, in my mind, this is what this hole is going to look like. And that is normally in our world about a 2 foot over dig. 2 or 3 foot is really common. So we're going to make the hole about 2 foot bigger on each side than the structure, so that when we get done, we have room to work in that hole. Okay, if that's the green hole is the area that we're going to dig out, what happens to all my red stakes? They're gone. I have no idea where they're going to go. When the excavator digs a hole and throws the dirt either in a pile or in the back of a truck to carry it out of there, all my stakes are going to be either in the pile or off to the spoil site. So what do? How do I give them the data they need without them destroying the data I give them? Okay, what we do is we set offset stakes and we make what we call the big box. Okay, a box is the rectangle that circumscribes the structure. So if I drew a box, that box right there goes around the whole structure. But once again, I can get myself in a position where they destroy those stakes. Now, we use offset, they call them offset stakes. We pick a number, and 5 is an awful common number. 5 foot. Make the big box go around this box that's 5 foot bigger on each side. So we come out here 5 feet. I'm going to go a little farther. We come out here 5 feet. Come out here 5 feet. And come out here 5 feet. And we make a box that goes around that 5 foot so that when we dig, so here's 5 foot, that'd be this side. 5 foot, that would be this side. 5 foot would be this side. And 5 foot would be this side. Now there's one stake, there's another stake, there's another stake, and there's another stake. Now all those stakes are at 5 foot larger than a box that would circumscribe the house itself. Now look where my stakes are. There's only 4 of them. They're out of the way. And when he digs, he doesn't have to worry about running them over, digging them up. When the hole's done, the stakes are still there. The people who are setting the forms for the foundation know what the offsets are. They can come in and drop that box into the hole and lay it out so it's perfect. So this is offset. These are 5 foot on a test or a set of drawings. It'll indicate 5 foot is a very common number for an offset. So that building is what? 58 foot long? 58 foot long. So my big box is going to be 68 foot long. And the width of it, 40 foot wide. 40 foot wide, so 10 foot, 5 on each side. My big box would be 50 foot long or wide, 68 by 50. So I go out and I'm going to lay these stakes out. They're going to come off of some control. Property corners, center line of road, things like that. Okay, if I lay a box out that's 50 by 68, is that possible right there? Could I end up with a box that looks like that? I'd say yes, that's a parallelogram. Do I want the corners of my foundation to be anything but 90? No. So the big box needs 3 dimensions. It needs an offset width, an offset length, and a square up dimension. Once again, if you happen to have that Scale Master Pro or the Construction Mate calculator, it's a very, very, very simple calculation. And it is pretty simple on, if you have a TI or something like that, it's simple too. But what do we got here? If I want that to be a 90-degree angle, if I measure the diagonals of this guy, doesn't look like the diagonal 1 is a lot shorter than diagonal 2. Okay, you got 2 ways of doing this. I've seen it done both ways in the field. One is if you have a calculator, you can calculate that distance. It'd be 50 squared plus 68 squared square root. A squared plus B squared equals C squared. So if I did that, 50 squared plus 68 squared equals the square up distance squared. So I'm going to turn it on and clear it. Clear 68 squared, 4624. Plus 2500, 7124. If I take the square root of 7124, okay, clear. Square root of 7124. 84. .40379. That's 84 feet. Minus 84 times 12, 4. And so if I went to the field, I want that to not be a parallelogram, but to be a square. I would have 3 dimensions in my pocket. One would be 50 foot for square up for the box offset width, 68 for the offset length, and 84 foot 4 7/8 for the square up dimension. And I can lay those out now and end up with a dimensionally correct shape with angles that are 90 degrees instead of something different. So that's the big box. The big box is a box that goes around the whole circumscribed structure. So here's the line that goes around the whole structure that makes a rectangle. My big box is 5 foot larger on each side. So find the width, add 10 foot, 5 on one side, 5 on the other, and you're done.